Thank you for having me. It's super nice to be here. I would like to talk to you today about machine learning and quantum computing, but I promise it's super high level. There isn't a lot of math. Now, suppose you have a task, and your task is to build a machine that can recognize cats. And the first thing you can do, of course, is to use your human-made representation of a cat and try to encode this into your machine. So a cat is a furry animal that has pointy ears and it looks very cute, and you try to encode this into your machine, which basically amounts to writing a giant if statement. So you have if input sample contains animal, it has pointy ears, return cat. The problem is you would need to do this for every cat everywhere, and you need to do this for every object everywhere. And this is not a super scalable approach, because if there is some genetic mutation somewhere and cats are suddenly fluorescent green, your program will not be able to recognize cats. So another thing you can do is let your own machine build its own representation of a cat. And this representation might not be interpretable or understandable to us humans, but it allows the machine to recognize cats if the input contains one. And nowadays, this is of course done using deep neural networks. Just to be very precise, we call them neural networks, but they have nothing to do with neural networks in human brains. They're just a mathematical abstraction of what happens in brains. And essentially, these models are composed of neurons connected by weighted connections. And these weights are like knobs that we can tune in such a way that the machine will be able to recognize cats in the end. We do this, of course, by feeding a massive data set of cats and dogs and planes or the entirety of the internet if you're interested in language. And we feed this into the deep neural network. We define some form of a cost function which quantifies how much the prediction of your model is different than the ground truth, than the actual labeled cat. And based on this cost function, we optimize the weights. So we tune them using gradient descent or backpropagation to be very precise. And in the end, it turns out that these models are able to recognize cats or speak to us like a human would, or fold proteins, or play Go with superhuman abilities. So this approach ended up being super powerful in the last decade or so. Now, of course, the key ingredient here is hardware. The story usually goes, machine learning exploded because we have a lot of data and we have fast algorithms and we have fast compute. And this is true, but it's not very precise. It's true that we have a lot of data. Thanks to communication engineering in the last 50 years, we have wireless networks, we have the internet, we have the Internet of Things. And it's true that algorithms are relatively fast. And this is specifically true for backpropagation, the training algorithm. And hardware is fast, but with respect to specific operations. And that is matrix multiplication. So GPUs, the hardware that we use today in deep learning, were originally developed for gaming. And they happen to be really good at multiplying matrices. And neural networks, and I would argue even more importantly, backpropagation, can be very efficiently represented as matrices. So the success of deep learning is in some way serendipitous, which kind of raises the question, well, what happens if we don't have these types of machines? So we don't have a machine that can push around zeros or ones, so a Turing machine. But we have hardware that can maintain a linear combination of zeros and ones. And this is, of course, a quantum computer. Now, formally, a quantum computer is just a collection of qubits, right? A qubit is a physical entity that can maintain a superposition of states. And we want to manipulate these qubits with a quantum circuit, which essentially defines our quantum algorithm. The quantum circuit is technically comprised of gates, and these mathematically need to be unitary operations. In practice, it means, for example, you're trying to shoot lasers at your qubits, and you try to manipulate their quantums. Now, why unitaries? This is most of the math you'll see today. So imagine you have some random variable, nothing quantum there, you have a coin, and your random variable can take two values. So you have two random observations, heads or tails, so 0 or 1. If you have a random variable, two coins, then the observations that you can see are 0, 0, 0, 1, 1, 0, 1. Nothing quantum there. Each of these observations have a probability mass function attached to them. And if you want to manipulate this probability mass function into a different probability mass function, you need to apply a stochastic matrix. This is a channel which ensures that the probability mass function that you obtain satisfies the axioms of probability. So if you have a probability distribution, you want to obtain a different probability distribution, which is still a probability distribution, you have to apply a stochastic matrix. Now, if you take the square root of this probability mass function and you do a bit of linear algebra, you write your vector as a superposition of unit vectors, or a linear combination of unit vectors. You can call them basis states if you want. And furthermore, you allow these entries to be complex numbers. So unlike in classical probability, where the entries in your vector are strictly real positive numbers, here you allow the entries to be complex numbers, such that the square of the magnitude of this complex number now represents the original probability. So now you get a real positive value if you take the square of the magnitude of the complex number. This is still a probability distribution. And if you want to manipulate this type of probability containing this complex value into another probability that still satisfies the axioms of probability, you need to use a unitary matrix. So this is just a motivation why you need to use, mathematically at least, unitary matrices to manipulate qubits. So we have this vector of complex numbers that represents a distribution because the sum of all entries of squares of magnitudes equals to 1. This is Born's rule. If you want to manipulate these types of vectors and obtain a new vector of complex numbers that satisfies the same properties, you need to use a unitary matrix. This is just what happens mathematically. Of course, if you are experimentalist or interested in experiments, then you do, for example, some laser manipulation of the state of your qubits. Once you have your state of complex values, if you want to obtain some observation from a random variable, you need to apply a measurement operator formally. This means, again, you apply a unitary matrix with a particular structure. But this means that in the end, you obtain classical values. So if you had two qubits, you get two random bits in the end. You can get 0, 1, 1, 0, or 0, 0, or 1, 1. So from two qubits, you get two random bits. There is no gain in resources in this regard. Well, the power of a quantum machine essentially lies in how we manipulate this quantum state. So what the unitary actually does to this vector of complex values. And now is probably a good time to have the talk, because we've all read how quantum computers compute everything at the same time. To be precise here, what a quantum computer does, or what a unitary does, is it creates an interference pattern such that the amplitude, the complex value of the correct solution, is magnified and everything else is suppressed. So let's say that you are trying to find the energy levels of your qubits representing atoms in some molecule, and you have options energy level 0 or 1 for each of your qubits. You have 2, and the correct solution is 0, 1. A successful unitary design, so a successful quantum algorithm, will be able to magnify the amplitude of the correct solution 0, 1 and suppress everything else, such that when you measure your quantum state, you get 0, 1 with high probability. Now, at the risk of adding one more questionable analogy out there, but my formal background is in electrical engineering, and what design of quantum algorithms reminds me of is designing interference patterns in beamforming. So we have this problem. Every device around, every phone has an array of antennas. And basically our problem is to design an interference pattern between these antennas such that the received radio frequency wave at the base station is with high signal to noise ratio. So we want to suppress the noise, we want to amplify the signal. This we do via control of interference. In a quantum algorithm, remember we have a superposition of states. We want to control interference in such a way that we get to amplify the amplitude of the correct solution and we get to decrease the amplitude of everything else. And this is basically the power of any good quantum algorithm. And in fact, most of the known quantum algorithms with established performance guarantees, like think of Grover here, leverage the properties of interference. The problem is they assume access to very reliable quantum machines that are very large scale. So we have 1 million qubits available, they're very reliable, and we can compute anything we want. Nowadays, we do have quantum computers available, right? But they're relatively small scale. So we have around 100 good qubits we can do computation with. And they're relatively noisy. So we don't really know what we can practically use them for. However, and this is for the coders amongst us, they're very easy to access. So these are tools that we have, which we can easily access. We can write code for, because most of the libraries available are PyTorch or TensorFlow based. The syntax is relatively accessible, I think. So we can try to solve these types of problems relatively easily. And with this, we kind of have most of the ingredients to do machine learning with quantum computers, where the key idea is that some of these unitaries are dependent on a parameter. This parameter represents some rotation angle of how you rotate the qubits on a Bloch sphere. But this is a parameter that can be tuned. So in principle, it can be learned based on data. So the workflow of quantum machine learning is very similar to the workflow of classical machine learning. We have data. We try to encode the data into some quantum state. We define some cost function that tells us how different the prediction is from the ground truth, labeled cat. And based on this cost function, we try to optimize the parameter of the unitary. And in this way, in principle, we can do machine learning with quantum computing. So for this, for machine learning, quantum or otherwise, doesn't matter. We need data. We need to define the model architecture. In our case, this means that we need to define the unitary, the sequence of gates, or the quantum algorithm, if you will. We need to define a training procedure, or rather, we need to choose a training procedure, and then we need to train, test, validate the model. This is it's almost identical to classical machine learning, right? And any machine learning task can be approached like solving a Lego puzzle. It can be argued that machine learning has been so widely adopted because it's relatively modular. You have the cross entropy, and you can take the cross entropy and apply it to a convolutional layer and a recurrent layer and whatnot. And you have these building blocks you pick and choose from, and you make up your bespoke model for the problem you're trying to solve. The story is very similar in the quantum case, except we have fewer building blocks and not so many efficient training procedures. First, the data. In the quantum case, the data can be either classical data, think of images of cats and dogs. And this type of data need to be encoded into a quantum state. You can choose whatever encoding procedure you want to follow. The most widely adopted takes the features, so the pixels of cat, let's say, and tries to encode those values into rotation angles. Or you can have quantum data, so you can operate on a quantum state directly. So say you did some quantum experiment, maybe you deployed a quantum sensor, you try to estimate the phase of something, and the phase perturbed your quantum state. And now you want to learn from the quantum state directly, without having to measure it and then feed it again into some new estimator or a learning outcome. And in principle, there is a theory that says this is where the largest gains from quantum machine learning lie, because a classical computer cannot access the quantum state directly, right? Whilst a quantum machine can. Once you have your data, of course, that means on the problem you're trying to solve. If you're trying to classify cats and dogs, your data is images of cats. But once you have your data, you need to choose the architecture of your model. This means that you need to choose the sequence of unitaries that you apply to the quantum state. The simplest thing you can do is take the so-called mean-field model, whereby you take single qubit gates and you just place unitaries on each qubit that operate on each qubit independently. And this is not that powerful as an architecture, but I would argue this is one of the most important models in quantum because it's a really good benchmark. If you have your quantum algorithm and it performs well and you want to see how well it performs, and you take out all of the 2-qubit gates, you get a mean field model. And it turns out your benchmark performs equally well. Well, in that case, you don't need to bother with 2-qubit unitaries, and you don't need to bother with a quantum computer, maybe, because separable models are much easier to simulate on a classical device than models with 2-qubit gates. If this is not enough, which is likely the case, then you can move on to adding multi-qubit unitaries, for example, 2-qubit unitaries. And these types of gates operate on multiple qubits simultaneously, here 2 qubits. And particular types of gates, like C0 or CX, are relatively efficiently implementable on hardware. So we call this the hardware efficient model, because we can implement them nowadays. And with this, you get the so-called hardware efficient answers. And in my experience, at least, these two are a really good place to start. And it turns out the second one was super helpful when we tried to train classical binary Bayesian neural networks. Now, these types of models, Bayesian binary neural networks, are classical neural networks. So we are trying to learn on a classical device. And these types of models, instead of weights, have a distribution over weights. And we try to draw samples from this distribution, and these samples represent the weight of the model. In the binary case, we usually have to place some Bernoulli distribution, and we try to find the parameter of the Bernoulli distribution. And then we sample from the Bernoulli, take the outcomes, and use them as weights of the neural network. Now, this is relatively limited in terms of the number of problems you can solve this way. So what we did is, instead of the Bernoulli distribution, we used the quantum circuit. So remember, we measure the qubits and we get binary values, so zeros and ones. We take the outcomes of the measurement and we use them as weights for the classical model. So learning is done on classical hardware. We have a task. We're trying to learn the task with a classical neural network, but we sample the weights for the neural network from a quantum circuit. And the motivation was, well, we know that classical neural networks are really good at handling high-dimensional inputs, high-dimensional outputs, but we also know that a quantum circuit is, at least in principle, really good at sampling, because all you need to do is make a measurement and you get samples from whatever distribution you have. And if you combine these two, so you do learning on a classical device, but you get the weights from a quantum device, it turns out it's better than using a Bernoulli distribution and trying to learn its parameter.
Sorry, yeah. So does the quantum device do you need to feed the data also?
No. So you do need to learn the parameters of the circuit, but you don't need to feed the data into the quantum circuit. You feed the data into your classical model, you get the prediction from the classical model, you define the cost function as from the classical model, but you take just the weights from the quantum model. And if you use the free energy and you do a bit of manipulation there, you will see that the only thing that you're feeding data into, it's sufficient to feed the data only in your classical neural network. You just have the distribution. Think of a Bernoulli distribution when you are trying to train a Gaussian or a Bernoulli. You don't really feed the data into your classical distribution, right? You just have the parameters of the distribution, sample from that, get the weights.
So using the quantum computer as like a random number generator.
Yeah, exactly. Yeah, and we literally get random numbers, right? Random outcomes of measurement. But the hope was that if we find good parameters from the quantum circuit, it can be at least better than the Bernoulli distribution.
So if I may ask, in the classical model, you said the weights are random variables.
Yeah.
Are you then simulating the whole exponentially large distribution?
Yeah, so the weights are random. Each weight is an outcome of a measurement of the quantum circuit. So you need to have, in the quantum circuit, you need to have as many outputs as weights in your classical.
Okay, so you run, I would picture you run the classical network sequentially, and every time you ask the quantum computer what the weight of every, all the quadratically many weights, you have to sample them using the quantum computer.
Right, yeah, this is a Bayesian model, so you have to sample, right? How many times? Yeah, depends on the problem, but it's definitely more than one. So to get a single prediction, it's enough to sample once and run your model once. But if you want to do uncertainty quantification, then you need to sample.
So one run of your quantum circuit outputs as many random numbers as you have weights.
Yeah. You take the weights, plug them into the classical model, do a forward pass, get a prediction. And if you're satisfied with that, okay. If you want to do uncertainty quantification, do the same thing again.
Right.
Yeah.
Thanks.
And if you have defined your model, let's say you chose one of the two, we need to find the parameters of the circuit. And for this, we can use, in principle, gradient-free or gradient-based optimization. Now, if we have 3 parameters that we are trying to find, then it's okay. We can use something like Nelder-Mead, and it's likely to converge. But if we have more than 3 gates, then the only option is gradient-based optimization. The problem here is that we don't have a training procedure with the same efficiency of classical backpropagation. So what we use is called the parameter shift rule. This is a version of finite difference differentiation, except it's an exact rule. So this is not an approximation. What you do is you take the parameter you are interested in, you shift it to the right, let's say by pi-half. You run your model, compute the cost function. Then you shift the parameter again to the opposite side, again by pi-half. You run the model, you get the cost function. You take these values of the cost function, take the difference rather of these values, normalize by something, and you get your gradient. So to get a single gradient of a single parameter, you need to run the circuit twice. Twice if you're making a decision using one outcome of measurement. If you're making a decision using the expectation of the outcomes of measurement, which takes 1,000 runs, then you need to run the circuit 2,000 times for a single gradient. And if you have many, many gradients, of course, this is not super scalable. And let's say that you can do that, you don't care, and you can sample as many times as you need to. Well, the more serious problem is that your gradients will disappear. So you will hit some place in the optimization landscape where all of the gradients are 0. And of course, if your gradients are 0, you can't do anything. You can't do gradient descent. And this is because models like the hardware efficient circuit happen to be very expressive. This is in principle a good thing. And expressive models means that you can fit many functions, which is what we want. But in quantum, there is a clear trade-off. The more expressive a model is, the faster you hit this barren plateau in terms of system size. If you have many qubits, it's very fast to hit this landscape where you have no gradients. And again, backpropagation is really problematic. Rather than lack of backpropagation is really problematic. So you can do gradient descent, but your gradients might disappear. Unless, and this is where we come to a probably familiar concept, we use symmetries in our model architecture. I promise no group theory here, but symmetries, coming from the ancient Greek symmetria, meaning same measure, have been around for a very long time. Plato thought that the Platonic solids were the building blocks of the universe, right? And since then, symmetry has been everywhere across art and architecture and science. Some people claiming that it's the way by which we create order, meaning, and perfection throughout history. And of course, you can find it in art if you go around exhibitions. The last one I saw was at the Tate Modern. There have been symmetric buildings since the dawn of times, right? Think of the Colosseum or the Pantheon. All of these are highly symmetric. And there's even theories in psychology about why us humans want symmetries connected to uncertainty reduction, because brains don't like uncertainty, right? And if you see half of a building that's symmetric, you know what the other half looks like. But anyway, in science, it has led to some of the major discoveries in the last few centuries. And some people even claim that physics is essentially the study of symmetry, which may or may not be true. But in machine learning, quantum or otherwise, symmetry is definitely one of the central concepts because it represents prior knowledge. So an inductive bias that we try to encode in the choice of an architecture, such that if we do this well, we can generalize better, or we can have fewer steps of gradient descent. Or in the case of quantum specifically, we can actually have gradients, so we don't hit some barren plateau. On the classical side, there are many examples of symmetry-preserving models. Think of convolutional neural networks, graph neural networks, transformers, which are the backbone of ChatGPT and AlphaFold. All of these are symmetry-preserving models. On the quantum side, we also have models that can preserve symmetries. We have quantum convolutional neural networks or quantum recurrent neural networks. Again, to be precise here, we call these quantum neural networks. They're really nothing similar with classical neural networks, and definitely not similar with neural networks in human brains, but we have adopted these terms, so you'll see them. Now, what does it mean to encode symmetries present in data? Well, suppose we have two types of data. The first one is an image, and the second one is a molecule. And images, for example, live on grids. They are Euclidean data, right? So the relevant symmetry here is translation or shift. Because you can shift this image however you want, you can shift it to the left, to the right, it's still the same image. You can flip a picture of a cat upside down, it's still a picture of a cat. And we want a model that is capable of preserving these types of transformations. And it turns out that convolutional layers classically are exactly capable of doing this. And on the quantum side, we also have a quantum version of a convolutional model. And this is essentially a quantum circuit that is capable of preserving these types of transformations. So we have a translation equivariant convolution, which is essentially comprised of particular 2-qubit unitaries placed in a particular manner. And then we have a pooling operation, which essentially measures subsets of the qubits until we are left with one in the end. And this guarantees invariance in the end to translations or shifts. Now, if you have a molecule, molecules are very easily represented as graphs, right? And in a graph, order has no meaning. So you can take the nodes in your graph, you can order them however you want, and this doesn't mean anything. So graphs are equivariant to permutation. Think of energy levels in molecules again. If you permute the atoms, the energy levels do not change. Or think of achievable rates in communication networks. If you permute the devices, achievable sum rates do not change. And we want some model that is capable of preserving this type of transformation. And it turns out that graph neural networks, quantum or otherwise, are capable of doing exactly this. And even transformers, to some extent, are capable of preserving this transformation. On the quantum side, we do have quantum versions of graph neural networks. And these types of unitaries are dependent on the structure of the graph. So you have your graph, it has nodes, it has edges. And then when you want to build the unitary, you essentially place 2 qubit gates wherever you have an edge. So each node is represented by a qubit. Then if you have an edge between 2 particular nodes, you add a 2 qubit gate. And a specific subtype of this is the SN equivariant model, whereby you essentially add 2 qubit gates with the shared parameter to each pair of qubits. Essentially, this corresponds to having a fully connected graph. So you have edges everywhere and you add 2 qubit gates everywhere. And these models are in the end invariant permutation. And it turned out they are particularly useful in simulation-based inference. So in simulation-based inference, what you want is to train a simulator. And this simulator simulates some physical process. For example, a digital twin.
Hi. Hoor je me nu wel? Ja. Volgens mij is er toch nog wat fout gegaan. Want ik moet ook hier een wachtwoord invullen. Terwijl je eigenlijk je activatiecode in moet vullen. En even kijken. Bij de mailinator zou hier het e-mailadres moeten staan.
Oh, okay.
Sorry.
I think it should be okay. Yeah. So in simulation-based inference, we are trying to find the simulator of the world. And this is a parametric model, so it's some mechanistic model. And we want to find the parameters of this simulator. For example, in machine learning, you are training a model that tries to classify pictures of cats, but you have just 3 pictures of cats. And that's not enough. You want to find some simulator of cats that gives you more images of cats. And this is very relevant if you work in biomedical domains, whereby you have 3 MRI scans, and only some of them have labels because you have biopsy results for one of them. And you want to find more data that is from the same ground truth distribution. And to do this, you need to train a simulator. So what we thought is, again, we know that quantum circuits can sample from some distributions. What we thought is that, well, maybe the quantum circuit can be a good simulator. And of course, here you are restricted to domains in which the data has binary features, right? We can get 0s and 1s. So your data can only have binary values in the feature vector. And we want to train this simulator to give us more data such that we can train some model on the data that we get from the simulator. And 2 particular tasks we considered are one with image generation and the other one with molecules. So one model we considered was the quantum version of the convolutional neural network and then the graph neural network. In the first task, again, restricted to binary features. So what we could do is have some data set of bars and stripes. You know, if you have a bar or if you have a stripe in an image, you have a 1 there and everything else is a 0. And in the second task, we wanted to generate primary structures of molecules. A primary structure of molecule is essentially the structure of covalent bonds. So if you have 2 atoms and if you have a covalent bond between them, then you have an edge in your graph. So you have a 1 there in your data sample. If you don't, you get a 0. And it turns out if you use a convolutional neural network, quantum convolutional neural network for the first task, and the quantum version of a graph neural network for the second task, you get distributions that are resembling the ground truth distribution. And this is true compared to the case when you use something like the hardware efficient model or the separable model. The separable model is really, really not good here. But these models that can reflect the symmetries that we know are present in the data are capable of providing relatively better results. Of course, the problem here is the training procedure, but yeah, there are ways to go around it. Now, all of these were examples of spatial symmetries in a way, but a lot of the data we get from nature are sequential, right? We have sequences of vital signs or sequences of the state of a network or a communication network or whatever. So the question is, how can we use symmetries in sequential data? Or really, what is the relevant symmetry for a sequence of data sets? And to find one, the first thing we need to know is that, well, sequences are a result of sampling a continuous signal, right? Everything in nature is continuous. Vital signs are continuous, traffic is continuous, that we sample at particular time points and we get discrete sequences. The problem is, of course, we can't really control the sampling rate in many of the cases. Think of an intensive care unit where you go to check vital signs at particular time frames. And even more, the clocks that we use are sometimes jittery. So it's not the time step in which we get the data is not very precise. And it turns out if you take different sampling rates from the same signal and you feed these two sequences into a recurrent neural network, for example, you get different results. And that doesn't mean, it doesn't make much sense because it's the same signal. We just change the sampling rate and suddenly we can't do any learning tests. So time warping invariance is formally a way to be able to be resilient to changes in sampling rates. We want to be able to have a different rate and still accomplish the learning task. Formally, time warping invariance is a differentiable continuous function of time. The simplest case is when it's just a linear transformation of time. So you multiply something with a constant. And this essentially means you either stretch or shrink the time axis. So when you, let's say you stretch the time axis, so when you sample the signal, you might get some repeated observations. And formally, time warping invariance means that we want to have a model class such that for input x of t gives us an output z of t, but for a time warped input, x of c of t gives us an equally time warped output, so z of c of t. And models like classical recurrent neural networks, for example, do not have this property. And this is also true for the quantum version of a recurrent neural network. And the quantum version of a recurrent neural network now has a repeated application of the same unit. So formally, it is comprised of two subregisters of qubits, subregister A and B. And we encode data only in subregister B. So at time step t, we encode the data sample x of t in this register B. Register A represents the memory of the system. So these are qubits that are never measured. So at time step t, we encode the data into register B. Then we let these qubits interact with the memory via a unitary. And then we measure only subregister B. So the first subregister is never measured. The idea is, in this way, it can essentially retain information from the whole sequence, or rather from the data samples that came before x of t. And the training procedure is the same. So we measure the qubits, we define some cost function, we get using the prediction, and then we try to find the parameters of this unitary. And again, we apply the same unitary for each time step t. And this model happens to be not invariant to time warp. It's really sensitive to the type of sequence you feed it. A time warping invariant counterpart to this model, and if you want to do some math, it's in the reference, but it turns out a time warping invariant version will apply this unitary with probability alpha. So with probability alpha, you apply the unitary. With probability 1 minus alpha, you do not apply the unitary. It basically means you do not change the state of the memory qubits. And this probability alpha happens to be equal to exactly the derivative of the time warping function. So you have the time warping function, you have the derivative, and this is the probability with which you apply this unitary. It tells you how much information your model needs in order to make the next prediction. It doesn't need information from all of the sequence. It needs information probabilistically from some parts of the sequence. The problem is, of course, you don't know the time warping function. We never do. So what we did is use just a basic recurrent layer. And the job of this recurrent layer is just to learn the probability alpha. So this is just a single layer recurrent model with a sigmoid in the end. And this sigmoid represents the parameter of a Bernoulli distribution. And from this Bernoulli, we draw samples. If we get 0, do not apply unitary. If we get 1, apply unitary. And this is trained again end-to-end. It's trained in the same way. You get some prediction, define some cost function, try to find the parameters of the unitary, and try to find the parameters of the gating mechanism. And again, the meaning of this is that you need to know how much information your model needs in order to make the next prediction. And we do this via the gating mechanism. And there are also stochastic versions of this model. So in a stochastic version, instead of trying to take the expectation of your observation, you make a prediction using a single observation. So you try to make a prediction using 0, 1, or 1, 0, 1, 1. So you need to have a discrete domain of predictions, and using a single outcome of measurement, you try to make a decision, essentially. And the time warping invariant version of this model is the same. So you have this gating mechanism that tries to find the probability, tries to learn the probability. And then with this probability, you either apply the unitary or you.
Sorry, but like if you apply this unitary probabilistically, doesn't it mean that your state will become very mixed at some point?
Yes. Yeah. So.
And doesn't that mean that it's sort of, you are going to be very close to classical in some sense?
I suspected it might be the case at some point, which is why we eventually did compare to classical models, but it turns out this is better than a classical.
Is it better? Like
lower prediction error. So if you try to get the prediction error over time and you accumulate all of the prediction errors, the one with the quantum models is lower than a classical LSTM. And this is true for the invariant version and for the non-invariant version as well.
they do have like a comparable size of, like, I guess in the quantum model, you have this memory that has some number of qubits, and I guess you want that in a classical case when you compare it to have similar size.
So
like it is because you can, I don't know, like I think there are several parameters that are being trained.
yeah. So the size of the model is not exactly 1-to-1. We have 6 qubits in the quantum regime, and in the LSTM, we try to have the same number of parameters in total to have some kind of a fair comparison, but it's not really fair, I suppose. Though I guess a transformer is a useful benchmark here, but then a transformer with 12 parameters doesn't make much sense. Yeah. Yeah, so these were results for one task. The first one was trying to predict classical signals. So this is just a sine wave. And if you warp this signal using a linear warping function, it means that essentially you get repeated observations 1/8 times. And we want to predict these types of sequences for various levels of warping.
So, like, I mean, if this warping is linear, shouldn't you just do Fourier transform and forget about all the neural networks?
In principle, you can.
Or is the idea that you want it to work also when the warping is non-linear?
That's the next example. So the linear warping case is the simplest thing that can happen. So you have a constant and you multiply time with a constant. But this definition of time warping assumes and can admit any warping function. It can be linear, it can be non-linear, it can be anything.
But like, I guess what I'm saying is that presumably you expect this model to be useful in the regime when it's non-linear, because in a linear case, you would just.
I think so. Yeah, the linear cases are more like toy experiments or like peace of mind results.
It's like, yeah, just to check that it's sanity check.
It's basically a sanity check. And it's also, if it doesn't work on the linear case, then it's kind of hopeless. Yeah, so what this says is essentially that the time warping version of a recurrent model can fit these types of sequences, whilst the time warping variant version of a recurrent neural network cannot fit the time warp sequences. And this is again expected because the memory is modified in a custom way when we have a time warping invariant. This is true for an LSTM versus an RNN, and it's true for a time warping invariant quantum recurrent model versus a generic recurrent model. So an LSTM, by the way, is a time warping invariant model, but a recurrent neural network is not. So a recurrent neural network cannot preserve these transformations, but an LSTM can. So if you compare this with a recurrent neural network, in theory, it should be way worse.
So if I may ask, the task here is of remembering the cosine wave, does it mean they have to reproduce it?
So the task is to remember the final sample of the cosine wave. So you feed cosine wave x of t, you want to get x of t minus 1.
Okay.
And in the next task, you want to predict. So you feed x of t, you want to get x of t plus 1.
Okay.
And you want your model to be able to do both. And this is an example of nonlinear warping. So now we are trying to predict. So now we're trying to get future samples. And this is a 3-qubit open quantum system, and we want to predict the dynamics. And first we have the dynamics as a function of t, and then we use square of t. So our time warping operation is nonlinear, it's square of t. And the same conclusions hold. It turns out if you give these types of sequences to a quantum recurrent neural network, it's not going to be able to perform so well. The interesting thing here is that the LSTM is actually better than the quantum recurrent model. But the time warping invariant counterpart is capable of fitting this sequence a bit better. And whilst the math says that the gating mechanism needs to learn exactly the derivative of the time warping function, what happens in practice is a bit different. So we get something that's close to the derivative, but it's not exactly the same. And we suspect that in this way, the model can compensate from some approximations made in the derivation. But yeah, this is a hypothesis at this point. Okay, so just to be precise here, time warping invariance is not really a formal symmetry. So I can't give you a group, I can't give you actions. This is more of a peace of mind result in the sense that this is essentially class invariance. If you have a model that can fit a particular sequence, then you want a model from the same model class to be able to fit a warped version of your sequence. So you don't need to go looking around for different architectures. And time warping invariant models essentially do that. So if you have a time warping invariant model, it can fit some sequence, then you change the sampling rate. This type of invariance tells you that the same model can fit the warped sequence. So it's immune to these changes of sampling rates. You might need to retrain your model for a different sampling rate. Though zero-shot transfer is also possible, so you use the same model. Most importantly, in the quantum case, this is a restricted model class. And because of this, your gradients shouldn't disappear that quickly. So you should get some gains in trainability. Okay, so now we chose the model, we trained the model, we need to test and validate the results. First, we need to choose appropriate benchmarks, of course. And I think that separable models are a really good place to start. So you choose whatever unitary you need, you solve your task, then you just remove all of the 2-qubit gates and try to test against that model. Train your new model, test on that. If you get results that are comparably good, then excellent, you can use the simpler model, or at least you have a really good benchmark. Also, sometimes it's useful to compare with classical models, though again, how you find the hyperparameters of these classical models is not so easy to determine. Unfortunately, we don't have the MNIST of quantum machine learning, so we don't have some golden, yeah. Oh,
5 minutes.
I'll be done.
Okay.
Thank you. We don't really have the MNIST of quantum, but this is work in progress, I think, and hopefully we'll have a data set that we can all use. And this is a good analogy. So you have all of your models with some strengths, some weaknesses, and you put them in a race against each other. Though I like the relay version of this race, whereby you identify the strengths of each model and you try to put them together into a new model to solve your task. Okay, so finally, we tested the model, and I guess now is the time for another version of the talk, and that's what do we use them for? Well, in my view, quantum machine learning for now is fundamental research. It's curiosity-driven work. We basically do it because it's fun, and that should be completely okay, at least in academia. And this is because, one, we don't have a scalable training procedure, and that's the key to a learning algorithm. And two, we don't know the role of scale. If you think, neural networks have existed since the 80s, but it wasn't until 2010 when ImageNet came out, they blew them up, and they saw that deep neural networks can generalize. This is because shallow models with few parameters can hit some version of a barren plateau. We didn't know about double descent until 2010. Turns out you blow them up and suddenly they can generalize, even though you expect them to overfit today. So we don't really know what happens when instead of 50 qubits, we have 1,000,000 qubits. But of course, it's always useful to look at some tasks that are suspected to be difficult for classical algorithms. Now, the question is, what is difficult for a classical algorithm? And if recent Nobel Prize winning lectures are any indication, some tasks that we thought are difficult for classical devices, turns out there might be actually solvable. So the argument is, if there is some pattern, then a classical neural network, a pattern matching system, will be able to find. And also, AI, classical AI is getting better. So as we are getting better, the benchmark is also moving further and further along. So things are becoming very, very difficult. But something with a clear benchmark, and again, as someone from an engineering background, estimation problems are really interesting to me. And this is one with a clear benchmark, is resolution in metrology. We know that the sensitivity of classical imaging or sensing devices is limited by quantum mechanics, right? The limit is very clear. So perhaps there is a way to use these types of circuits to try to find some states that are metrologically useful. And eventually we might be able to improve the resolution of imaging or sensing. And on that, I'm going to stop. Thank you. And if you have any questions, please.